So often we humans like to bask in all the wonderful things we've accomplished, especially our scientific discoveries. And there's nothing wrong with that. But it's often far more valuable to ask ourselves what we don't know. After all, ignorance is the birthplace of endeavour, the spark behind every question that's ever changed the world. And we have so much left to learn. From the mysteries we know we don't understand, to the far more unsettling kind. The secrets the universe keeps from us without us even realizing. The unknown unknowns. So grab a snack, pour yourself a drink, and settle in, because you don't want to miss this episode of Dark Beacon. Everything we don't know about the universe. There's no reason the universe has to be the way it is. If the force of gravity were just 1 part in 10 to the 60th stronger, stars would collapse the instant they formed. 1 part in 10 to the 60th weaker, and they'd never ignite at all. That's the same as throwing a dart from one side of the observable universe to the other, and hitting a single atom. The strong nuclear force that binds atomic nuclei is balanced to a precision of 1 part in 10,000 billion 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 billion. If it was slightly weaker, hydrogen would be the only element. Slightly stronger, and every atom would fuse instantly into iron. No chemistry, no planets, no life. Every constant we know, from the mass of the electron to the speed of light, sits on a razor's edge, each one tuned to absurd precision, as if the universe were coded rather than born. So what explains it? One idea is the string theory landscape. The notion that there aren't just a few possible universes, but 10 to the power of 500, each with its own set of physical constants, each bubbling into existence from the quantum foam. We just happen to live in one of the rare universes where the numbers make sense, because only here could anyone be asking the question. That idea leads to the anthropic principle, the philosophical safety net of cosmology. It says the universe looks fine-tuned because we're here to notice it. A dead universe can't ask why it's dead. It's elegant but circular, a cosmic shrug disguised as logic. Others invoke cosmic natural selection, where black holes give birth to new universes, each one slightly mutated, slightly different. A Darwinian multiverse, where the constants evolve over countless generations until they just happen to produce stars, galaxies, and eventually us. And then there's the more unsettling possibility, that fine-tuning isn't chance at all, that the universe is a kind of self-correcting system, a simulation perhaps, designed to sustain observers, not for benevolence, but because without observation, the code can't run. Each theory stretches the limits of science and sanity. But the question remains, why this universe? Why these impossible numbers balanced to more decimal places than we can count, all so that atoms could assemble into eyes, and eyes could look back at the stars that made them? The universe may be fine-tuned for possibility, but that doesn't explain how atoms started to think, how lifeless chemistry turned into biology. The best attempt we've ever made to recreate that moment came in 1952 in a small lab at the University of Chicago. 2 scientists, Stanley Miller and Harold Urey, tried to simulate the conditions of the early Earth. They filled a glass apparatus with methane, ammonia, hydrogen, and water vapor, the gases then believed to fill our planet's primordial skies, and sent electrical sparks flashing through it to mimic lightning. They ran the system continuously for about a week, electrodes crackling, gases swirling, the liquid slowly turning a murky red-brown. When they analyzed the contents, they found something extraordinary. Amino acids, the basic building blocks of proteins and the raw alphabet of life itself. It wasn't life, but it was a whisper, a glimpse that under the right conditions, nature could write her own code. Later research showed that Earth's early atmosphere might have been less reducing than Miller and Urey assumed, but even so, experiments using updated gas mixtures, ultraviolet light, and volcanic energy have yielded similar results. In other words, the chemistry still works, we just haven't found the full recipe. And here's the thing, their experiment ran for a week. Earth had hundreds of millions of years, trillions upon trillions of lightning strikes, countless coastlines, volcanic pools and deep oceans, each one a chemical laboratory running blind experiments for eons. Given that timescale, even a 1 in a trillion chance becomes inevitable. That's just one theory. Others push the story deeper. Some scientists point to hydrothermal vents on the ocean floor, natural reactors where mineral-rich water and intense heat create constant chemical gradients. There, energy and complexity flow together. We found entire ecosystems thriving around them today, cut off from sunlight entirely. Proof that life doesn't need a gentle planet, just chemistry and power. Others favor panspermia, the idea that life, or at least its ingredients, arrived from space. Meteorites like the Murchison stone have been found containing dozens of amino acids, some older than the Earth itself. If life's chemistry can form in the vacuum of interstellar dust, then the universe might be primed for biology everywhere. And then there's self-organization, the idea that complexity itself is alive, that once matter reaches a certain threshold of energy and information flow, order arises naturally. Life as a phase transition, not a miracle, but an emergent property of the cosmos, like ice crystallizing from water when conditions are just right. Whatever the truth, one fact remains. For the universe to know itself, something had to open its eyes. And somehow, against impossible odds, a ball of molten rock learned how to dream. Somewhere along the chain of evolution, life did something astonishing. It started noticing. Neurons began firing not just to move or eat, but to feel. And from that silent circuitry emerged the strangest phenomenon in the cosmos, experience, the awareness of being. Science can map the brain in exquisite detail. We can watch thoughts form, emotions flicker, decisions ripple through billions of cells. But no equation yet explains the one thing that matters most, what it feels like to be you. This is what philosophers call the hard problem of consciousness. How do physical processes inside the skull give rise to the inner world of color, sound, love, and pain? How does matter wake up? Some researchers believe it's an emergent property, that when information flows through a system with enough complexity, awareness appears automatically, like heat from fire. Others go further, arguing that consciousness is fundamental, the base layer of reality itself. According to theories like integrated information or panpsychism, every particle carries a spark of subjectivity, and the mind is what happens when the universe organizes itself into a mirror. Quantum physicists have even suggested that observation might play a role, that consciousness and reality are somehow entangled. Not that we create the universe by looking at it, but that the act of observation is woven into its fabric. And then there's the evolutionary view, consciousness as a survival tool, an inner simulation engine that lets creatures test futures before they happen. If that's true, then every dream you've ever had is a continuation of the oldest experiment in biology. We still don't know which, if any, of these ideas is right. But this much is certain. The moment awareness appeared, the universe stopped being silent. Atoms built eyes. The cosmos looked back. And for the first time in 13 billion years, something wondered why. For more than a century, physics has spoken two languages: Einstein's general relativity, the grand architecture of the cosmos describing space and time as a smooth, flexible fabric, and quantum mechanics, the microscopic dance of particles and probabilities. Each one works perfectly in its own domain, but put them together and the math explodes. At the heart of a black hole, or the first instant of the Big Bang, both theories fail, space-time tears, infinity appears, and our equations collapse into nonsense. What we need is a single theory that unites them, a theory of quantum gravity. Some believe that answer lies in string theory, the idea that every particle is really a tiny vibrating string, and the universe itself is a vast symphony of invisible notes. In this picture, gravity isn't a force, but a vibration, a geometric echo rippling through higher dimensions beyond our perception. Others turn to loop quantum gravity, which treats space-time not as a smooth fabric, but as a woven mesh of discrete loops, Planck-scale threads of reality, smaller than anything we can imagine. In that model, space itself is quantized, built from the smallest possible grains of existence. There are even theories that gravity isn't fundamental at all, that it's emergent, a side effect of entropy and information, like temperature emerging from molecules in motion. But without experimental evidence, these remain mathematical dreams, beautiful, intricate, and utterly untested. To probe them directly, we'd need a particle collider the size of the solar system. So for now, we stare at black holes, hoping their whispers of radiation and gravitational waves carry clues from the edge of reality. Because somewhere, deep in that chaos, the laws of the very large and the very small shake hands. And when we finally understand how, we'll know not just what the universe is, but why it holds together at all. Every story we tell about the universe begins at the same moment, 13.8 billion years ago, with everything condensed into a single point of impossible density, a singularity, the Big Bang. But the deeper we look, the less certain that beginning becomes, because before the Big Bang might not be a forbidden question, it might be the key to understanding what the universe really is. Einstein's equations break down at t equals 0. Space, time, and causality stop behaving, but our mathematics have evolved since then, and they whisper possibilities. One idea is the quantum bounce. In certain quantum gravity models, the universe never truly begins or ends, it oscillates. Each Big Bang is the rebound of a previous universe that collapsed in on itself, a cosmic heartbeat, echoing through eternity. Another is eternal inflation. Our universe might be just one bubble in an infinite foam, each bubble born from the quantum fluctuations of the last. To us, it looks like a beginning, but in reality, the process has no start and no edge. Then there's Penrose's conformal cyclic cosmology. In that model, the death of one universe becomes the birth of another as the cold embers of the old cosmos stretch and fade until scale itself loses meaning and the next Big Bang ignites from the ashes of infinity. Others suspect there was never a before at all, that time itself is emergent, a property that appears only once change becomes possible. Before the Big Bang, asking when is like asking what's north of the North Pole. Whatever the truth, the beginning may not have been a flash, but a transition. From timelessness to time. From potential to existence. And if that's so, then the universe didn't start with an explosion. It woke up. Now, there's one mystery I know you've heard before, probably in every space documentary since VHS, but it still deserves a quick nod, because it's too big to ignore. Dark matter, dark energy. Between them, they make up about 95% of the universe. All the galaxies, stars, planets, even you fit into the tiny sliver that's left. Dark matter holds galaxies together. Dark energy rips them apart. And if that sounds confusing, that's because it is. We've given them names, but they're really just elegant labels for our ignorance. The cosmic to-do list of modern physics. And since you've probably sat through at least a dozen documentaries about them already, I'll respect your time and keep this one short. For now, it's enough to remember this. Even with all our telescopes and equations, we still only understand 5% of what's out there. The rest remains unseen, a reminder that the universe is still very good at keeping secrets. Every so often, the universe throws us something we didn't even know to expect. A discovery so strange it breaks the script, forcing science to rewrite its own story. The philosopher Nassim Nicholas Taleb called these moments black swans. For centuries, Europeans assumed all swans were white, until explorers reached Australia and found black ones. The impossible, suddenly, wasn't. In science, the same thing happens. We think the laws of physics are settled, until reality taps us on the shoulder and says, "Think again." It's happened before, when Newton's perfect clockwork universe shattered under the weight of relativity. When quantum mechanics revealed particles that exist in two places at once. When dark energy made the cosmos accelerate instead of slow down. Each time, what we thought was impossible turned out to be true. So what would the next black swan look like? A faster-than-light particle? Evidence that time can flow backward? A signal from outside the universe itself? Whatever it is, it will change everything. Because the universe still has moves we haven't seen yet. And the strangest part? We won't recognize it when it arrives. Because by definition, a black swan never looks like one until it spreads its wings. What if the universe we see isn't the whole story? What if reality has depth, layers we can't yet perceive? For most of history, the world seemed flat, solid, and simple. Now we know it's built from quantum fields, invisible ripples of probability, each one humming with energy even in the vacuum of space. But what if there's something deeper still? String theory hints at hidden dimensions, tiny, curled-up directions of space that our senses can't detect, but that shape every particle and every force. Other physicists see the universe as a vast information system, where space, time, and matter emerge from quantum data, like a hologram projected from some deeper code. And then there's the unsettling possibility that we're inside that code, a simulated reality so detailed that even its creators couldn't tell the difference. These ideas sound like science fiction, but so did black holes once, and time dilation, and the Big Bang itself. If there are hidden layers of reality, then our instruments might already be brushing against their edges, in quantum entanglement, in dark energy, or in the mysteries we mistake for randomness. Maybe we're not discovering the universe at all. Maybe we're remembering it, one layer at a time. What if the universe isn't just a stage, but a participant? For centuries, we've imagined reality as something fixed and objective, a grand machine ticking away, indifferent to our presence. But the deeper we look, the harder that story is to tell. In quantum experiments, particles behave differently when observed. Photons act like waves until we watch them. Then they choose a single path, as if awareness itself flips the switch. Some physicists call this the observer effect. Others see it as coincidence, an artifact of measurement, not meaning. But the question lingers. Does the act of looking change what we see, or does it create it? The philosopher John Wheeler once called it a participatory universe, one where reality isn't fully real until it's observed. and the cosmos evolves through that constant feedback between consciousness and matter. It's not proof of simulation, or spirituality, or anything mystical, but it does hint at a truth both humbling and strange. The observer and the observed may not be separate things. Maybe the universe isn't a story being told. Maybe it's a conversation, one that only exists because we're here to listen. For all our questions, all our telescopes and theories, the greatest mystery may not be out there at all. Maybe it's the one asking the questions. We search for meaning in the stars, but perhaps the universe is doing the same, learning about itself through every mind that looks up in wonder. Some call it consciousness, some call it God, some call it the simulation waking up. But whatever name we give it, it's the same impulse, the cosmos trying to understand its own reflection. Every discovery we make, every mystery we unravel, is really the universe studying itself through borrowed eyes. And maybe that's why we'll never reach the end, because the observer and the observed are the same thing, forever chasing their own shadow across the fabric of time. The deeper we look, the less we find solid answers, only deeper layers of wonder, folded into mystery, folded into us. Maybe the final unknown is that there was never anything to find, just the infinite act of looking. Thanks for watching, guys. A lot of work goes into these videos, so please leave a like and a comment. It really does mean the world to me.